Proteins are important to us because we're made out of proteins, and essentially everything we do is mediated by proteins. Things we do consciously, and just all the things that happen in our bodies. And that's true for all living organisms. So the proteins in nature carry out really a wide variety of different functions. And the whole premise of modern protein design is that with computers we can design new proteins that do new things. Once we understand the fundamental principles, design proteins which mediate even wider variety of types of functions, in particular things that are useful to 21st century humans. The Open Phil grant is just fantastically enabling. It's aimed at supporting two areas of work here at the Institute for Protein Design. The first is aimed at a universal flu vaccine. So we're all aware that flu is a major problem, and that current vaccines are not perfect in that you need a new vaccine every year, and in some years the current vaccines just are not very effective. So we're coming up with completely new ways of designing flu vaccines, taking advantage of the new protein design methodology we've developed here at the Institute. The second area is just as important and perhaps more fundamental. It is focused on improving the core computational methods for designing proteins. The applications of protein design today are not only to vaccines, but to a wide range of therapeutics, and outside of medicine to new biomaterials, perhaps nanoelectronics, and new ways of doing computing. The second part of the Open Phil gift is to push the methods forward to the point where we can really transform all of these different areas. In science, it's easier to get funding for sort of things that have clear applications today. So if you're going to solve a problem at this moment, but longer term efforts really aimed at sort of core transformation of an area or a field are much harder to get funding for. And so what's really unique about the Open Phil gift is that it will let us really dive deeply into the real core of our methods development and push it along in a way that we just never could have done without the gift. Up until very recently, when people wanted to make a new protein to carry out a new function, for example, catalyze a chemical reaction for which there wasn't currently a catalyst, what they did was they looked around in nature for a protein that already existed that they could modify a little bit. It's sort of, we make an analogy between this up until recently the only way of engineering proteins to early human technology, for example, in the Stone Age, where if you needed to solve a problem like dig a hole, you looked around for a bone and maybe tweaked it a little bit to make it better for digging, or sharpened a stick to make a spear. So the really unique thing we're doing here is, rather than making new proteins by looking around in nature and then modifying the one that looks closest, we're building proteins from scratch, from first principles, and that's what's really unique about what's going on here. The universal flu vaccine would protect you against a very broad range of flu strains. Right now, there's a projection that's made before each flu season, or maybe 6 months before each flu season, about what strains of flu are likely to be coming through, and then a vaccine is prepared specifically against those strains. But those predictions can be wrong. So if you had a universal flu vaccine that protected you against all flu strains, then it would take this guesswork out of the equation. And also, if you had a vaccine that gave you really long-lived protection, then it could be more like the other types of vaccines. We get a polio vaccine once, other vaccines we get once. You wouldn't have to keep getting a new vaccine every year. The really unique thing we're doing here is we're building completely new proteins from scratch, from first principles, and that requires a vast amount of computing time. And we wouldn't be able to do this work without volunteers who participate in the Rosetta at Home project. They donate their computing time to us. We send out the jobs, the protein design jobs. They send us back results. We end up using those results to decide which proteins to synthesize in the lab and test. And without their contributions, we wouldn't be able to design proteins. So this is the disulfide cross-link? And is it 2 homocysteines?
Exactly, yep. I think one is L and one's D. So
Yeah, but there's one over there too. Yeah, so that's actually not so bad.
Yeah, it's got like a little.
That one's
over
probably
there.
not. That one probably doesn't count. I think
Yeah.
Yeah, that's kind of cool.
Yeah, the forward folds are over on the side.
But they look
Yeah.
reasonable.
Yeah, they look really good actually.
Yeah. I guess if it does cross-link, it should be pretty good.
Yeah. If it's either locked or not, or like if